Hello and welcome to CMG's webinar on Advanced Integrated Analysis Features in CMOST. My name is Anjani Kumar. I'm the Vice President of Engineering Solutions and Marketing at CMG. I'm pleased to introduce Alex Novleski, a Senior Reservoir Simulation Engineer who will be presenting today's webinar. Alex holds a Bachelor of Science degree in Oil and Gas Engineering from the University of Calgary and has been with CMG for 7 years. Alex is the domain expert in simulation of unconventional oil and gas reservoirs, hydraulic fracturing, optimization, and uncertainty analysis. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. However, you may submit your questions at any time using the chat window on your screen. We will post the recorded presentation to our website within the next 24 hours. Please log in using your CMGL username and a password to access the material. Over to you, Alex.
Hi everybody, and welcome to our webinar today. So today we're going to be going through the Advanced Integrated Analysis features in CMOST. I'd like to begin with some of the basics of CMOST. So CMOST is our CMG software that works with our reservoir simulators to perform 4 main tasks, which is sensitivity analysis, where we're trying to figure out how the different inputs into our simulation models affect the simulation results. History matching, where we're trying to calibrate our simulation models by adjusting some of those inputs to match up with some of your measured or field data. Optimization, where we're looking at adjusting some of the operational controls in order to improve recovery in our reservoir or to reduce the costs. And then finally, uncertainty assessment, which we use to quantify uncertainty and see sort of what range of results we should expect given some of the uncertainty in our inputs.
At this time, I would like to pose a question to the attendees. Soon you will see a question pop up on your screen. And the question is, how often do you use CMOST in your reservoir simulation? There are 4 options that you can opt for. The options are regularly, sometimes, rarely, and never. I'll just give a few seconds to wait for the response, and the responses are showing up. Actually, it's a very, very mixed response here. Is 29% say never, 27% rarely, 27% sometimes, and around 18% say very regularly. So it looks like we have a very, very mixed group of audience today attending the webinar. So hopefully for people who have not used CMOST before, as well as people who regularly use CMOST, some of these advanced features that Alex will be talking today, you will find it extremely valuable, and hopefully this will lead to a better and efficient use of CMOST in your simulation work.
So CMOST has been updated continuously since it was released in 2009. So recently we've added in a bunch of new features, such as being able to manage multiple studies, our interactive proxy dashboard, which I'll be looking at a little bit later in the presentation, continuous parameters, parameter correlations, user-defined time series, as well as external engines. So in today's webinar, we're going to be going through 6 main topics, looking at proxy modeling and how that can speed up some of your workflows, looking at more complex objective functions, going past the basic objective functions, advanced parameterization, optimization options, data visualization, and as well, we'll take a sneak preview of some of the upcoming features in the 2016 release. So the first topic that I'd like to go over is looking at proxy models. So when we're running our reservoir simulation studies, oftentimes we want to get the most information out of the simulation in the shortest period of time. However, as many of you are aware, simulation can be computationally expensive, and it can take quite a while for a simulation to run in some instances. With proxy modeling, we try to link together some proxy models or some approximations up to the simulation to be able to quickly provide us our simulation results. So in this process, the simulation would be used as a basis. And on the right-hand side here, we can see a case where we're looking at adjusting well spacing and injection pressure in an optimization study. And we want to see the impact that that would have on the overall NPV. So we start off by running a few cases based on an experimental design and see how the inputs respond to the NPV. And then we can use a proxy model to fill in the gaps between those and quickly allow us to make estimates at well spacing and injection pressures which we have not simulated. So with this, we can quickly find the optimum value, or we can try out sort of any scenario we want within seconds. So most commonly when we use proxy modeling in CMOST, it's often used with sensitivity analysis. And on the left-hand side here, we can see some of the results of that sensitivity analysis, where we can determine which parameters have the greatest impact on the results. As well, the proxy model can be used for making further predictions without needing to run additional simulations. It can be used in some of the proxy-based optimization algorithms to quickly find an optimal solution. And you can even export these proxy models outside of CMOST for making further calculations. Another advanced feature that uses proxy modeling is our proxy dashboard. This is an interactive tool that allows us to make real-time predictions for all of our simulation results at once. So for example, here we have cumulative gas produced from a well versus time. And we can see as we make adjustments to some of the inputs, we can automatically see that pink curve move to show the response that we would expect from the reservoir. This allows us to quickly investigate the impact of parameters on the simulation results. Another area that we've developed further in the proxy modeling area is Sobol and Morris analysis. Oftentimes when we're looking at the simulation sensitivity analysis results, we find that the reservoir response is often nonlinear or could be dependent on multiple parameters. This makes it very difficult to model with conventional equations to describe these trends. We've added in Sobol and Morris analysis, which allows us to represent these complex relationships in a more simplified manner, looking at the overall effect as well as the variance of that effect. So for example, with Sobol analysis, we present the sensitivity analysis results as a percentage of total effects based on all of the parameters. So comparing to the traditional tornado plot that we see on the left, we can see that we get a lot of information listed out all at once, and it can be a little bit difficult to determine the impact of each individual parameter since there's interaction as well as nonlinear terms. When we go towards the Sobol analysis, we can quickly determine the most sensitive parameters based on their percentages. So in this case, we can see that the permeability in regions 5 and 6 of this reservoir have the greatest impact on the overall production from the reservoir. Another way of viewing these types of results is through the Morris analysis, where we can determine the average effect of each parameter, as well as the variability of that effect as we go from low to high values. So if we look on the x-axis of this plot, as we move more towards the right, we can see which parameters are more sensitive or have greater impact on our results. And as we move up the curve, we have more interaction or more nonlinear response based on the variability of that response. So in this instance, we can see parameters 9 and 10, which correspond to the permeabilities in regions 5 and 6, would be the most sensitive parameters. So I'm just going to go into a quick demonstration to see this in a real life case. So this particular example is from an unconventional tight oil reservoir where we have a couple hydraulically fractured wells in the reservoir, and we want to see how the different inputs into the reservoir, such as permeability or relative permeability changes, actually impacts the overall production. So this case has already been run through. In this case, we have 15 parameters, and we've run 65 simulations to begin with. So I'll first take a look through the sensitivity analysis results through the results and analysis section. And we'll first look at the impact of the parameters on the cumulative oil production. So the first thing that we want to see here is how accurate our proxy model is. So this quick verification plot allows us to see whether or not the predictions made from the proxy model actually match the simulation response. And by looking at this plot, most of the points are falling towards this 45-degree angle, giving us greater certainty in our response. So I'll switch over to the tornado plot, which is the more traditional analysis method using proxy models. And we can see that our highest sensitivity parameters are listed at the top. But in this case, you can see that permeability, or the horizontal permeability, is listed multiple times, making it more difficult to see the overall impact. So next I'll go to the Morris analysis, where we can see the further right the parameter is, the more impact that parameter would have on the cumulative oil produced. So here we can quickly identify that the horizontal permeability has the greatest impact by far over the other parameters. So other parameters that have an impact would be the oil relative permeability, as well as the permeability in the hydraulic fractures. With the Sobol analysis, we can see the results as a percentage of the overall impact. And once again, we can quickly see that horizontal permeability has the strongest impact, followed by the oil relative permeability and the fracture permeability. Within the settings, we can also change the type of proxy model that we want to use. Here we've been looking at a polynomial regression type proxy model, but we also have an RBF neural network type proxy model, which allows us to see more of the variability in the response since it's an interpolation-based method. So I'll just build that proxy model, and once again, we can look at the same plots, but now that we're using a different proxy model, we can see more of the variability in the response shown on the standard deviation on the y-axis. And the same thing with the Sobol analysis. Now we have these additional red curves showing the interaction impact. Another area that we use proxy modeling within CMOST is through the proxy dashboard, which allows us to quickly make estimates on the simulation response. So I'm first going to start off by building the proxy model for this type of analysis. So in this case, I'll select the RBF neural network type. And then we'll start a starting set of parameter values to begin our study. So we'll just randomly select one and create that basis. So the first thing that we want to do is see how closely our proxy model matches with our simulation results. And we can see here that our simulation is matching it perfectly against the proxy model, giving us good certainty in our results. So now I'm going to switch over to the what-if analysis, which allows us to make predictions quickly. So in this case, we might use this for something like history matching, where we're trying to get the simulation to match up with our measured results with the blue dots. So here we can see we're producing a little bit too much gas, too much oil, and our gas-oil ratio is a little bit low. So first I'll focus on the total production by adjusting the horizontal permeability, and I'm going to reduce that until we're almost close to this results. We can see we still have a little bit too low on the gas-oil ratio, so I'm going to adjust some of the relative permeability parameters to be able to adjust that. So I'll increase the permeability to gas and reduce the permeability to oil so we can get a fairly close response. And we may have to make some additional adjustments to the total production. So I'll go back to the horizontal permeability and adjust that until we've got a pretty good match. If I'd like to actually run the simulation to confirm this prediction, I can add this experiment to the list of simulations. And next time that I start CMOST, this case will be created and run through the simulator. So next I'd like to look at some of the CMOST objective functions and see how we can customize some of these functions in order to make more complex analysis of our simulation. So by default, there's a few built-in functions that allow us to assess the results from our simulation, such as raw simulation results, where we directly see the results of something like cumulative oil or our production rates, history match error, which is used in history matching processes, NPV, which is often used in optimization processes, as well as some additional other built-in functions. However, these built-in functions can't cover all possibilities, such as varying tax and royalty regimes, which may depend on region, or new emerging areas of R&D that are too new to add into our software. One of the ways that we can get around this is by linking CMOST directly to an Excel worksheet, where the Excel worksheet can do the calculations to assess the simulation results. This can be used to incorporate things such as variable cost and price forecasts, royalty and tax regimes, and as well you can use some of the more advanced functions of Excel such as Visual Basic coding. With the link to CMOST, CMOST will automatically write the simulation results as well as the parameter values to the spreadsheet, and then will pass back the calculated objective function back to CMOST once complete. Another way that we can get around the customization of CMOST objective functions is through the use of Python and JavaScript coding. This can be used for both objective functions as well as defining parameters. Areas where we've used this in the past have been looking at 4D seismic chamber matching functions, where we're looking at thermal reservoirs and seeing how the steam injected moves over time. We can also use it for doing more complex calculations of NPV or other economic indicators. And in the example below, you can see where we've used it to define a parameter, where we define our whole relative permeability table using some loops and logical statements. We can also use some of this coding for defining user-defined formulas, which we can use in plots and objective functions. So for example, here I have a plot of cash flows over time, seeing my cash flows decline into the life of the reservoir. It also allows for more advanced functions such as numerical integration or differentiation, where we can calculate the area under the curve or the slope of the curve. With these, you can use either JavaScript or Python scripting, whichever one is more familiar to you. So here, once again, I'm going to switch to a quick demo so we can see how we can add in some of these advanced functions. So the first case, I'm going to look at some of the coding to generate a relative permeability table based on some of my relative permeability endpoints. So here I've switched to the parameterization section of CMOST, which allows us to adjust some of the inputs into our simulation model. We can see that we have some relative permeability endpoints already defined, such as the connate water saturation, the residual oil saturation, as well as the curvature for our relative permeability curves. And at the very end, I have my coding to generate my relative permeability tables. So I can scroll down to the code and we can see I've gotten all my coding for generating out my relative permeability tables. And I'll just do a quick calculation to see the end result of this. So we can see once the calculation goes through, I have my relative permeability table for my oil-water table, my water saturation versus relative permeability to water, as well as relative permeability to oil. So we'll switch to another example where we can use some of these functionality to define our plots as well as our objective functions. So I'll switch to the plotting area of CMOST where we can see how we can define some of these formulas to generate new types of plots. So the first type of plot that I have here in this example is a discounted cash flow versus time, where we apply a price to the oil produced as well as associate a cost with some of our costs in our reservoir. So we can define the types of simulation results that we want to use in this formula, such as the oil rate, as well in this case I have steam being injected, which is going to be a cost to me. And we can also use time variables, which allow us to apply a variable discount rate over time. On the right-hand side, I can see my code that I've put in, where I've applied a price to the oil production as well as a cost to the steam injected, and I discount this over time. We can also look at a preview based on our base data set, and we can see our cash flows are initially high and then decline over time. In the second example, I have an NPV calculation, which is very similar since it's also calculating cash flows over time, but the difference here is I can add in a new transformation which does the numerical integration versus time. This will allow me to calculate the area underneath the curve and sum up the NPV over time. So when I go into my preview here, we start off at 0 since I haven't included my capital costs, and then we increase that over time to calculate my NPV. I'll now switch to the objective function section where we can see how I can add in some advanced objective functions. So in this case, I want to link CMOST to an Excel worksheet, which I have brought up here. The things that we can see in this worksheet is I have a calculation of cumulative oil versus time and a calculation of cumulative steam versus time, which would be based on the simulation results. I can also do some calculations based on those inputs where I've included a variable price forecast as well as a steam cost forecast for calculating my overall NPV. In this particular study, I want to optimize the well pair spacing between my wells in the reservoir. So I've also included some of the parameter inputs from this data set. So here I've added in well pair spacing, and we can calculate an NPV per unit area. So now I'll go back into CMOST where we can see how that's linked all together along with CMOST. So the first thing that we would do is add in a new Excel sheet spreadsheet calculation into the advanced objective function section. And then we would define the worksheet that we want to use. The next thing that we would do is define where to take the objective function value from this worksheet. So here I have worksheet NPV and cell C29. When I go back into my Excel sheet, I can see the worksheet name at the bottom, NPV, and then cell C29 is where I want to take my final result from. The next thing that we can do is add in some of the parameter inputs into our spreadsheet if it impacts the calculation of the objective function. So here one of my parameters is well pair spacing, and we can select from any of the parameters that we've defined in this Excel sheet or in our CMOST study. And then we specify where we want this pasted into the data set. So here we're pasting it into cell C26. When I go back into my Excel sheet, I can see that that's located once again in cell C26. The next thing that we would want to do is put some of our simulation results into the Excel sheet, and there's two options for this. One option is for specifying a specific result at a particular time, or else the second option is to define a range of results. So here, since we want the cumulative oil produced listed out every year, we'll select the range of results or the time series option. So the first thing that we do is define the type of result that we want. So anything from our simulation can be selected, as well as the output frequency. Here we have every year, but you can also select every month or every day. And then the location to start pasting the data. So here we're putting it in columns B and C and starting at row number 7. So when I go back into my spreadsheet, I can see columns B and C starting at row number 7 is where I want to start pasting this data. So when CMOST links with the Excel spreadsheet, every time a simulation completes, this information will be pasted into the sheet and our objective function will be directly calculated. This information is then passed back to CMOST, which can be used in our optimization study. So another area that we can make adjustments is in the parameterization section where we're adjusting some of the inputs into our simulation model. With the simulation models, any data or any value in our data set can be set in as a parameter to adjust using CMOST. However, some parameters are a little bit more challenging to adjust, such as large arrays of data, such as our Proxy or permeability arrays, or tables of data, such as relative permeability tables. One of the ways that we can get around this is through the use of include file substitution, where we take sections of the data set and we copy them into separate include files. This allows us to switch out entire sections of the data set so that we can adjust things such as geological realizations, where on the right-hand side we have 3 sets of probable distributions in our reservoir, relative permeability tables, as well as other tabular inputs such as viscosity versus temperature tables, compaction tables, or any others. Another way that we can make large adjustments of large amounts of data is through the use of pre-simulation commands, which allows CMOST to link to other external programs for generating the data sets. So this can include things such as Geological Software, CMG's Builder program, or any other program that we can run from the command line. This can be used for generating things such as brand new geological realizations. We can calculate builder formulas to readjust some of our arrays of things such as porosity or permeability. We can regenerate relative permeability tables without the needing of coding. Or we can adjust things such as hydraulic fracture spacing in unconventional reservoirs. With the typical workflow, CMOST would directly generate the simulation model and then would run the simulation through the simulator. With the pre-simulation command, CMOST would first generate a temporary data set which would be passed to the external software such as the geological package. This geological package might make a complete new set of geological realizations or make some adjustments to the data set, and then it would pass that back to CMOST to be able to finish off running and assessing the results from the simulation model. So I'm going to go through an example where we can put together some of these features for looking at the parameterization of the data set. So this particular case is a thermal EOR reservoir where we have 3 wells within this reservoir. What we want to do is do a study where we're history matching this, and we want to be able to change out the geological realizations. So in this instance, I'm looking at porosity, and this is one example of a geological distribution. We have several others already exported from our geological package which we can switch out with this one. Another thing that I've also added into this data set is some formulas which will adjust permeability based on rock type in this reservoir. So with this formula, I first calculate out the rock type based on a porosity cutoff, where the values above a certain cutoff will be rock type 1, such as our clean sand, and then the values below the cutoff will be represented by our shale regions. Next, I have a formula to adjust permeability in each of these regions, which will be sort of distributed irregularly through the reservoir. So here I have 2 different permeability multipliers based on the rock type. So the first permeability multiplier will adjust the permeability in the clean sand regions, and the second permeability multiplier will adjust the permeabilities in the shaly regions. So with CMOST, we want to be able to switch out different realizations and then make variations on those realizations by adjusting the permeability based on rock type. So now we'll go back into CMOST where we can see how we can set up some of these different things that we want to adjust. So I'm going to go down to the parameters section of the data set, and I'll click on the builder icon, which will allow us to adjust some of the formulas defined in this data set. So the builder editor has come up here, and I'm going to go down to the section to adjust some of the builder inputs. Here we can see we can select between relative permeability tables as well as formulas. So I'm going to go to the permeability modification formula, and we can see the formula written out once again here with 2 different multiplication values. So first I'm going to add in the modification for the clean rock type, and I'll call this first parameter permeability modification for rock type 1. Next, I'll select the second multiplication factor, and I'll add that in as well. And this parameter I'll set as permeability modification for rock type 2. Now when CMOST runs, it will automatically switch out the value associated with each of these multiplication factors and adjust the data set accordingly. As well, you can see I can also change my relative permeability tables. So I can select different inputs such as my critical water saturation and add these in as different parameters. And when CMOST links up with Builder, it will regenerate the entire relative permeability table. I can also include things such as the curvature on the relative permeability tables, such as my oil relative permeability curve. So I'll call this parameter relative permeability to oil curvature. Okay. So once I've added in any of the parameters that I want, I'll save these changes into the master data set which is used as a template for creating new data sets. So we'll go back into CMOST and I can import those parameters that I just added into the data set, or I can now select the range that I want to apply to each of my parameters. As well, we also want to change out the geological realizations in this data set. So to do this, I'll go to the CMOST editor, which allows me to adjust some of the text in the master data set. So I'm going to go down to the section for my porosity array, which I want to be able to switch out in this particular data set. We can also see an array for permeability, which is also listed here. So first I'll create a parameter which will allow me to switch out the entire set of porosity values. So I'll right click on that and I'll say create an include file, which will take this section of the data set and copy it to a separate file. So I'm going to call this first include file porosity realization 1. Here you can also see that I can also create a CMOST parameter which allows me to switch out which file I want to use. So here I'll give a name to this parameter, which allows me to select the values to associate with this parameter. So I'll call this porosity realization. So in many cases, we also want to link together different sections of the data set which would use the same realization. So for example, permeability would also have a linked realization. We wouldn't want to mix realization 1 for porosity with realization 3 or 4 for permeability. We really want these all to be linked together. So we'll show another way that we can set up the parameters so that we can have linked realizations in the data set. So I'm just going to delete the parameter that I just added, and I'll show you another way to define the parameter for this case. Instead of adjusting the whole file name as a parameter, I'll select the value associated with the realization and turn that into my parameter. So I'm going to call the parameter realization number. And once this is switched out, I can make this realization 2, 3, 4, and so on, and CMOST will automatically select the correct file for me. I'll do the same thing for permeability. I'll turn this into an include file to begin with, so I'll call this permeability realization 1. And I can select the value there and turn that into the exact same parameter. So I'll select from my predefined parameters, which was my realization number. And now when CMOST changes out the realization number, it selects the correct data set, or the correct include file for both porosity as well as permeability. Any other values that we want to adjust in the data set, we can also turn into parameters, such as the KBKH ratio here, which we can quickly add. So I'll save the changes to this data set, and we can see that we've automatically added in those last two parameters. So for the realization number, I'm going to switch this to an integer type parameter, and I can add in all the numbers associated with my different realizations. So you can add in as many different realizations as you'd like. So in this particular example, the first thing that will happen is the realization will be selected and will be associated with the data set. This data set will then be passed to Builder, which will then make modifications based on the rock types for permeability, as well as regenerating our relative permeability curves. So the next area that we'll look at is some of the optimization algorithm options that we've incorporated into CMOST. So oftentimes when we're setting up CMOST, we may have multiple objective functions when optimizing our history matching. These can include optimization cases where we're trying to reduce costs as well as increase revenue. Or it may have history matching cases where we're trying to match multiple wells and multiple data types. With a traditional approach, we would create one single aggregated solution, such as our total NPV, or we would calculate a weighted average error for a history match. However, the weighting is not always known beforehand, so there may be some uncertainty in the cost and price and where those will be a year from now or further on. As well, the weighting for the history match error can be arbitrary, so we don't necessarily know how much we want to weight each well or data type beforehand. Or we may have cases where we have completely unrelated functions, such as numerical tuning cases where we may want to optimize both runtime as well as material balance error at the same time. It's more difficult to find an aggregated solution when these different terms have unrelated units. So what we've done in CMOST is incorporated a multi-objective function optimization approach, which finds a set of optimal solutions, which is a trade-off between each of the multiple objective functions. By doing this, we eliminate the need for determining a weighting or a value to associate with each objective function. We do this by assessing each of the different outcomes or the objective function values against each other and seeing which of the parameter or which of the objective functions are the set of optimal objective functions. So an optimal objective function would be an objective function which there's no set of other cases that have both or all objective functions having a more optimal value. So in this plot we can see we're trying to minimize both function 1 as well as function 2. If we compare case A to B, A is always better than case B since it's better in both function 1 as well as function 2. Along the Pareto front or the leader front, we can see that there's no case that is both better in both objective functions for all of these cases. In a more simplistic case, we'll look at a road trip example where we're trying to find the route between two locations, and we're trying to find both the fastest route as well as the route with the shortest distance. So when we compare route A and route B would always be a better solution than route A since it's both a shorter distance as well as a shorter time than route A. If we look at route B and route C, there's no route that's both shorter and faster than route B. However, route C is a longer distance, but it's faster than route B. So route C could be considered an alternative to route B, depending on how much weight we want to place on time and distance. So this leader front, or the Pareto front, provides us an ensemble of alternative solutions that may be better in either time or distance. So in a simulation example, we can look at a numerical tuning example where we're trying to adjust some of our numerical inputs into our data set in order to reduce our runtime. However, we also want to maintain a low material balance error so that we know that our results are accurate. So we've done this two ways in this example. One is using the traditional single objective function approach, and the second way is using the multiple objective function approach. With the single objective function approach, we ran 1,000 simulations, and we can see the best runs are located along this yellow curve right here. If we compare that to the multiple objective function optimization, we only had to run 500 cases, which is quite a lot less, and we see that we get a wider range of alternative solutions. This allows us to select how much weight we want to place on runtime or material balance error. So we may want to focus on a case with a fast time but a slightly lower material balance error. There's also the ability to add in optimization customization into your workflows. With CMOST, we regularly add in different optimization algorithms, which we've added over the years here, such as the CMG DCE optimizer, particle swarm optimizer, random search, one hypercube plus proxy optimization, and recently last year we added in differential evolution, and coming in 2016 we've added in the CMG Bayesian engine for history matching functions. However, there's also a multitude of other options in the literature, and new algorithms are always in development. What we can do with CMOST is allow you to create your own algorithms and be able to link CMOST directly to these through the use of an external engine. What this allows you to do is generate your own algorithm and then have CMOST linked directly to that algorithm. This external optimizer will decide which sets of simulations to run and then CMOST will actually generate the data sets, run them, as well as assess the results. These two programs will communicate back and forth with the optimizer selecting which cases to run and CMOST performing the analysis of the results. The way that this works is through the use of different files which are passed back and forth between the optimizer, which you would generate, and CMOST. So it starts off by having CMOST specify which parameters have been defined using it, and then the optimizer will select which cases to begin running with. CMOST will take in those cases, generate the data sets, as well as run them, and then it will pass the results back through a separate file. The optimizer can then read in that file and select which new cases it should run based on that. This process would continue until we found the optimal solution or if we reached a maximum number of simulations to run. Another area that we've been actively developing is in the area of data and trend visualization. With CMOST, we assess large amounts of data from our simulations, things such as the oil produced or how the parameters interact with the simulation results. However, there can be very large combinations of parameters and objective functions to assess for trends. With our recently released interactive data visualization tool, it allows for a quick overview of large amounts of this information. So there are several different types of plots that we can see with the interactive data visualization tool, which makes assessing the results much easier. Things such as scatter plots, scatter matrix, parallel coordinates, as well as the data histograms. So I'll just switch over to an optimization case where we can see the interactive data tool in use. So in this particular example, it's an optimization case where we're running a water flood and we're determining where to place our new wells as well as how to operate those new wells. So we've run our simulations and we've found our optimal solution, but we want to assess how we've reached that optimal solution. So I'll go into the experiments table section and launch the interactive data visualization tool. The first type of plot here, we can see our scatter plot, which allows us to plot one data type against another. So for example, we can select the location of the well that we're going to be adding in this study versus the total NPV from our reservoir. And we can see quickly, we can visualize the trend in the data that as we move towards the west, we seem to have higher values of NPV or more recovery from this reservoir. We can then switch between all of the different parameters and see the trends of any of those different inputs on the simulation response. Another type of plot that we have is the scatter matrix, which allows us to visualize all of the data at once. So for example, in this case, we may want to see how the parameters impact the field NPV on the lower right-hand side here. So as we scan over to the left, we can see which parameters have a greater trend in the data, such as this parameter, as well as other parameters related to the operating controls. We can also highlight the cases with the highest NPV, and then we can see the different combinations which led to that high parameter value. Another type of plot that we have is the parallel coordinates, which allows us to see how different parameters interact or are combined with each other. So here we have all the data at once. However, we may want to see the cases with a high field NPV. So I've selected the column for the overall NPV, and the rest of the columns correspond with the different parameter inputs. So we can see all of the cases with high field NPV have a low bottom hole pressure for well 1, as well as a low bottom hole pressure for well 2. We can also see the different combinations which allowed us to get some of these high NPV values by hovering over the sections below. There we can see which combination of parameter values were used together. The last type of plot that we have in the interactive visualization tool is the histogram type plot, where you can see how frequently the optimizer selected each of the different inputs. So as I go through, I can see that most of the time we were using the lowest range on the BHP for this particular well, and we can switch between any of the different parameters and see how frequently each of the selections was chosen. If you're not already aware, CMOST also allows a licensing multiplier, which allows you more efficient use of your simulation licenses. For example, with STARS datasets, we can actually run 2 STARS simulations while using CMOST, while only using up 1 STARS license. This allows you to run twice as many simulations as you normally would. With GEM, we also have the 2-to-1 multiplier, and with IMEX, we can even run 4 times as many simulations at once. This also applies to other licensing types, such as parallel licensing or Dynagrid. This allows CMOST to more efficiently utilize the licenses and more effectively take advantage of your simulation investment. If you're interested in some of the upcoming features in 2016, we recently hosted a CMG webinar showing the new robust optimization workflow along with probabilistic forecasts. If you're more interested in some of these upcoming features in 2016, I encourage you to visit our user area of our CMG website to be able to download and view these previous webinars. With the probabilistic forecast, it allows us to see what sort of distribution of outcomes we expect. And with the robust optimization, it allows us to get a risk-weighted optimal solution no matter what the true geological formation is. So with CMOST, we're able to complete more in-depth analysis more efficiently, especially through the use of the customization of the CMOST workflows, allowing you to further customize your objective functions and your parameters. With proxy modeling, it allows you to quickly make estimations without needing additional simulations, which will allow you to speed up your workflow and create more cases more efficiently.
At this time, I'd like to pose another question to the attendees, and soon you will see a question pop up on your screen. The question is, how often will you use the advanced features described in this presentation? The options are regularly, sometimes, rarely, and never. We'll just give a few minutes or seconds, actually, and the responses are coming. It's good to see that around 55% of the attendees do agree that they will look into using these features that Alex talked about today sometimes. Around 12 or 15% are showing that they will try to use it regularly, 10% never, and the rest are showing very rarely. So I hope in today's presentation, Alex has given you a glimpse of some of the advanced features that are available in CMOST. Now we will open up the forum for questions. If you have not submitted your questions already, you can do so now using the chat window on your screen. There are several questions that have come up, and I'd like to take them one by one. The first question is from Radu, and the question is, can CMOST be used to run sensitivities on stars two-way coupled with geomechanics?
So yes, we can run basically anything that you can run through the simulation can also be linked up with CMOST. So no matter what options you're using in the simulation, such as the coupling with the two-way coupling with geomechanics, all of the results will then be passed back automatically to CMOST.
The next question is from Ellie, and the question is, does the Proxy dashboard still honor the actual reservoir flow or physics? It appears we simply train the RBF neural network and minimize the residual errors.
So yes, it still does take into account the physics, since the proxy models will be based off of the actual reservoir simulation. So we start off with the reservoir simulation and we run enough cases to accurately train the proxy model, and then the estimations will be based off of those initial cases based on the true physics.
The next question is from Eric, and the question is it possible to use CO2 foam parameters like FM, mod, etc. as history match parameters? If so, how can this be done?
So once again, you can use really any of the inputs into the simulation model as a CMOST parameter. So all we would need to do is locate that particular section of the data set defining each of those parameters, and then we can highlight those parameters and set them in as new CMOST parameters, which will then be adjusted.
The next question is from Faisal, and the question is, in advanced functions, can we link an Excel spreadsheet with induced seismic events? If not, then how can I use CMOST to include seismic events in my model?
So possibly we would have to first be able to define those seismic events using the Excel spreadsheet. So if you're able to sort of couple that up with an Excel sheet, we can automatically pass back to CMOST. Where we've used this in the past is actually through the JScript and Python scripting, where we've actually written up some code for being able to link between the seismic events and our reservoir simulation.
The next question is from Watik, and the question is the probabilistic forecasting same to the uncertainty analysis where we obtain P10, P50, and P90 of the objective function?
So it's very similar, but we've sort of built on that. So we've adjusted the history matching portion to be able to more comprehensively assess the entire search range. So instead of having sort of focused history match solutions, which may have a limited range of probabilities, we've ensured that we're getting the entire range of the uncertain history matches, and that's used further in the uncertainty assessment.
The next question is from Husham Ali, and the question is, what is CMG DECE, when it can be used?
So the CMG DECE is one of the types of optimizers. It's an evolutionary-based optimization method which uses evolutionary algorithms to calculate the optimal solution. It can really be used in any of the cases that we're either history matching or trying to optimize.
The next question is again from Watik, and the question is there any way to update the reservoir model during the forecasting using CMOST?
So really any of the areas of the data set we can make adjustments. So whether we're doing a history match where we're looking at the historical period, we can make adjustments to the reservoir properties. Whereas in the forecasting, we may want to make adjustments into looking at some of our operational conditions so that we can optimize those.
The next question is from Anusha, and the question is, can CMOST import relative permeability values after history matching back into Builder?
So any of the data sets that are generated by CMOST are complete data sets. So what we would do is after we've done the history match, we would find our optimal solution, and then with that optimal solution, we can open that up directly into Builder, which will have those history matched relative permeability curves automatically there.
The next question is from Husham Ali, and the question is, can I use the advanced features for chemical reactions when I'm running chemical EOR model, and how?
So yes, we can include some of the chemical reactions into our CMOST workflow. Basically, we would just need to go into the components section where the reactions are defined, and any of the different inputs, such as your reaction rates, can be set in as new CMOST parameters.
The next question is from Jeremy, and the question is, can results from a completed CMOST study be used by another study?
So yes, we can copy complete studies, so we can copy everything. As well, we can also select bits and pieces from one study and copy those through another study through the import feature in CMOST.
The next question we can take is from Ellie actually, and the question is, when we do sensitivities, we usually hold the values of the predictors constant except for the input parameter of interest. Can we find the most optimum scenario in CMOST where multiple inputs or parameters that can you control are varied simultaneously?
So yes, we allow for actually both of those different workflows in CMOST. So the first workflow would be the one parameter at a time workflow. But the workflow that I showed with the different proxy models was based on modifying multiple parameters at a time. So you'll see the response surface methodology is the selection that you'll make. And these will modify multiple parameters based on an experimental design, and then a proxy model will assess that sensitivity.
The next question is from Saeed Husseini, and the question is, can we use spatial data as history matching data or in proxy tuning to match historic data? For example, let's say I have gas distribution along the wall at one specific time measured using logging tools, and I want to match that.
So yes, we can incorporate maybe multiple realizations of how this gas would be distributed in the reservoir, and then CMOST can select between those different inputs or even link up with a geological package to generate completely new inputs, which CMOST would then incorporate into the data set.
The next question is from Humayu, and the question is, could you explain the interaction effect in Sobol analysis and how it can help in our sensitivity analysis?
So with that, it basically uses the proxy model to assess the average effect of each of the parameters as well as the variation in that effect. So it'll run several hundred different sort of test cases using that proxy model to see how adjusting the parameter affects the outcomes. And then it basically does an aggregated analysis of all the different test cases and finds out what the average effect is, which gives us sort of the mean or the direct effect, and then sees the variation in that effect, which allows us to see sort of how nonlinear or how much interaction there is between multiple terms.
The next question is from Michael, and the question is, can you elaborate on the history match optimization using seismic for SAGD?
So with that, we would need to add in a function for assessing how closely the seismic measurements actually match up with the results from the simulation. So we would pick out a property such as temperature or saturation, which we can use to assess the location of the steam chamber in the simulation. And then we would need an interpreted seismic response, which we can compare to. And usually we would place that in a text file. We have developed some coding in-house in CMG for comparing those two. So if you'd like more information, I would encourage you to contact your sales representative, which would allow us to get in touch with you.
Thank you, Alex. At this time, I'd like to end the question and answer session. If your questions were not answered in this session today, we will approach you individually within the next 24 hours with your answers. I hope you have gained a better understanding of some of the advanced features in CMOST that Alex talked about and their application in computer-assisted sensitivity analysis, history matching, optimization, and uncertainty analysis. CMG do offer a multitude of training courses for all skill levels. For those of you who are interested in knowing more about CMOST, we frequently offer two-day courses, one focused on unconventional reservoirs like tight oil, shale gas, and any other unconventional reservoirs, and the second course focuses on heavy oil applications. We also offer company-specific customized courses on a variety of other subjects all around the world. For more information on our training course offerings, I invite you to visit our website at cmgl.ca. We will post the recorded version of today's webinar on our website within the next 24 hours. You can use your CMGL login and a password to access the material. If you have any other questions related to the material presented today, or would like to know more about the product offerings, please do not hesitate to contact us at sales@cmgl.ca. Again, thank you all for joining us for today's webinar on advanced integrated analysis features in CMOST.